Hello everyone. We already started discussing about microarchitecture concepts in the previous class. In particular, we started discussing about the execution steps that might take a single cycle or multi-cycles to complete. In the previous session, we focused on the basics and introduced single-cycle computer microarchitecture. Now we will continue our discussion on the single-cycle machine and introduce multi-cycle microarchitectures also. We shall also spend pretty decent amount of time on discussing the different types of control logic design. So let us start with the instruction memory. In the previous class, we talked about control word for the micro instruction of interest. We added 4 more control signals into the control word as shown. They are memory write, PL, JB, and BC signals for branch and jump instructions. So the control word becomes a 20-bit long word. We need to decode the given instruction specifications for the control signals. For the hardwired control, we will have to use combinational logic circuits to implement this conversion. Conversion meaning that conversion from instruction, particularly the opcode, into the control word, which is 20-bit long at this point. If you look carefully, we can basically tabulate the necessary control signals based on the function type and the bit indexes. As you can see in the top row, 15, 14, 13, 9, and also some of the control signals, associated control signals. As you can see that the destination register, the source register A, source register B, they are present in the instruction, so they're going directly to DA, AA, and BA. So this covers the first 9 bits of the instruction, and which is stored in the instruction register. Other than branches and jumps, we also observe that function select equals the 9th bit, 10th bit, 11th bit, and the 12th bit of the instruction. When we consider 15, 14, 13, and 9, we have this table as shown in the slide. In the very first column, you can see that we listed all these operations like memory read, memory write, branch on 0, branch on negative, and jump. And you can see that the corresponding bits, 15, 14, 13, and 9, and also the control signals associated with that. So if you just look carefully, you can figure out the simple combinational logic. You can alternatively draw Kano maps to see that also. So MB, for example, directly equals the 15-bit of the instruction, or MD is also directly equals to the 13-bit of the instruction, so on and so forth. However, here the 9th bit is also the last bit of the function select. In other words, the function select 0. So in order not to contradict with the function select functionality, we need to differentiate function select 0 from BC, which is equal to the 9th bit of the instruction. It can be observed that if we AND PL prime with 9th bit, we essentially be focusing on the functional unit where we use function select bits actively. Therefore, we set FS0 to 9 and PL prime, and the rest of the bits of the FS equals as described in the instruction 12, 11, 9, and 10 and 9th bit. So you have to be a bit careful about figuring out these relationships, and it requires a few minutes to discuss, and then come to a certain conclusion about the necessary combinational logic that is required to implement a certain functionality. Using careful type assignments and don't cares, it will yield very simple logic as shown in this slide. So we actually ended up with the pretty simple combination logic that decodes the instruction into 20-bit control word. This basically completes the design of the single-cycle simple computer. Here are 6 different instructions given as examples. Adds an immediate constant to the source register, and the result is written to the destination register. A load instruction uses the contents of source register as the memory address of the operand, and the result is transferred to the destination register. You can also go over the rest of the instructions and understand what they do using the function column. One other thing is the corresponding control signals we need to generate for each of these instructions. And these are listed as the last 7 columns of the table in this slide, namely BD, MD, RW, MW, PL, JB, BC control signals. Well, in the next slide, we will start showing the ISA control signals and the data paths for ADI, LD, and BRZ instructions. And the rest of the instructions will be left for you to exercise. So here's the add immediate instruction. Zero fill is used to make 3-bit operand 16-bit number, and it gets added with source register A, and the result is written back to the destination register. Note that the contents of source register B is used as the source of the constant operand value. The picture here in this slide also shows the control signals that need to be generated for this instruction to be executed correctly. For example, the opcode turns out to be 100010 in order to add immediate instruction to be initiated. Also, MB, FS, MD, RW, MW, PL, JB, and BC control signals are also shown in this slide. Similarly, in the LD instruction, the source A register holds the address of the data to be loaded. The contents are given as the address to the data memory, and the data output is going through the MUX-D, and finally gets written to the destination register. The write enable signal must turn 1 for the register file to complete writing the output of the operation to the destination register. The control signals are also shown in the figure. Finally, the BRZ instruction is shown, and it's a conditional branch operation which is based on zero condition. So using the instruction formats we already talked about, it's of interest to tabulate all the operations that the ISA can support, and this is actually given in the previous class, but I'm just going over it. For the next slide will be the class exercise, so that's why it's here also. The opcode determines the operation. If you remember, here's the table. This table shows the single-site computer ISA capable of executing all these instructions. Zero force stands for zero fill operation, actually ZF. It's not zero force, it's zero fill. M is the memory, and SE notation is for sign extension logic. The table shows both arithmetic and logic operations supported by the ISA. It's usually best practice to look up the opcode and description of the given instruction rather than memorizing it. So for the next in class exercise, it's recommended that you look up whatever you're looking for in this table, and then try to solve this question. And this question is asking you to use the previous table to figure out the values that is stored in the memory location 250 after executing all the instructions listed left to the memory table. The complexity of the instructions are dependent on the specific operations that they perform. For example, a polynomial equation solver, or think of a root finding instruction. These instructions could be relatively very complex compared to simple logic or arithmetic operations. When the complexity of the operations increase, it becomes very hard to complete the operation in a single cycle. On the other hand, if the same physical memory is used to read the instruction as well as write the data, we will then need at least 2 clock cycles to complete the operation. Remember that this is called Princeton architecture, and unlike Hardwired architecture, there is only one single memory for both instructions as well as data storage. Finally, consider the worst-case delay path of all the operations supported by the microarchitecture. The clock frequency as well as the rate of operation will be limited by the single cycle. The multi-cycle computer design is a remedy for the first 2 concerns. However, it will not solve the last concern, since we will have to wait multiple cycles to see one instruction fetched, gets executed, and result to being stored. However, maybe we do not need to wait and fetch instructions every clock cycle. So we need to be careful about each stage being utilized by only single instruction execution. This technique is called pipelining, and it can address the third issue listed in this slide. Here's what we mean by execution delay. As you can see, varying degrees of delay is associated with each of the components of the data path. As you can see, the most time-consuming stages are memory read and memory write operations. The components of the data path is selectively used by different instructions, and the one that is drawn here is the worst cycle. When we observe the total delay in this example, It's about 9.8 nanoseconds. This means that the worst case execution delay, which is 9.8 nanoseconds, that will put a limitation on the maximum clock frequency achievable. Because otherwise you will not be able to get this instruction executed correctly. If you do the math, the max frequency in that case then will be 102 megahertz. I mean, beyond which the computer cannot go because of the limitation that is imposed by the most time-consuming instruction, execution. Since using a single memory requires at least 2 clock cycles, then Princeton architecture must be multi-cycle. So let us use a single memory for both instructions and data. So let's adopt Princeton architecture for the moment before we develop our microarchitecture for multi-cycle execution. This assumption is not essential to the multi-cycle design, by the way, but it's done here to illustrate the basic concept. Since we use single memory, this would require a new mux m with control signal mm to select the instruction address from the PC, the program counter, or the data address. In addition to that, it would require a new path from memory data out to the instruction path in the control unit. This new instruction path is drawn and shown in blue, and it directly goes into the instruction register. It is clear that to hold operands between different cycles and independent cycles, we need additional registers. Remember, our previous data path had 8 general purpose registers. Now we add 8 more, and they are temporary storage registers now, to the register file. Register file now becomes 16 by 16. Addresses to the register file increase from 3 to 4 bits now. Register file addresses come from the instruction itself for the storage resource registers like 0 to 7, indexed by 0 to 7, or also, I mean, it could also come from the control word, the temporary storage register in particular, 8 to 15. The control word specifies the source for register file addresses. So we add register address logic to the register file to select the register address sources. 3 new control fields for register address source selection and temporary storage addressing are DX, AX, and BX. We must also hold instruction over the multiple cycles to draw on instruction information, throughout the instruction execution. This would require an instruction register to hold the instruction. If multi-cycle operation is used, then we need to load the instruction at the beginning by turning on the control signal for the instruction register, which is labeled here by IL. On the other hand, multi-cycle operation requires the addition of a hold operation to the PC, since it only counts up to a certain point and then to obtain the NIV instruction. NIV encoding for the PC operation uses 2 bits now rather than 1 in order to control micro operations over multiple cycles. If you also consider the control logic, the inputs to the control logic are opcode status bits, as similar that we have seen similar phases when we designed a single cycle micro operation. But the control logic now, unlike single cycle, now has control state that's going in, and the outputs are control word, through modified data path and control unit. It's necessary to use the state information for the control because it would need to produce the right set of control signals for each cycle, and it could be different from one cycle to another. We use another register to store the control state and combinational logic to generate the control word, both sequencing and data path control parts of the circuit. Here NS is used to represent the state, and PS is used to control the program counter at each operation cycle. Here is 28-bit long final code word. Actually, it's control word for the multi-cycle implementation. DA, AA, and BBs are replaced by DX, AX, and BX because now we need 4 bits. And MM field is new. For the sequencing control, we have new control signals like IL, which controls the loading of the instruction register. PS, as we said before, controls the operation of the program counter. And NS gives the next state of the control state register. NS is picked to be 4 bits, which means that we control 16 states. We assume it's 16 states, which is viewed as adequate for this design. You can also increase or decrease it based on your design, so you can use less number of bits. So far, we have seen hardwired control logic and its implementation, and this control logic is completely combinational and works pretty fast. Also, it provides a single cycle execution of the control. However, it's hardwired, in other words, manufactured once and only once, and cannot be changed or reprogrammed. This inflexibility brings the burden of a new design. If the ISA changes or new instructions are added to the current architecture later on, plus as the number of instructions increase, the microarchitecture that is supposed to support it becomes more complex. So an alternative control model is known as the microcoded control, and which is the preferred method when the instructions get complex. In that model, control words are stored in memory, called controlled memory or control store. Next state is usually computed, which makes it very flexible and allows multi-cycle execution of control. This flexibility made microcoded control very well suited to complex instructions. However, since it uses memory, microcoded control is usually slower. Machines today use a combination of both hardwired for simple instructions and microprogramming or microcoded control for complex instructions. Microcoded design differs from hardwired design in that the control logic gates are replaced by a memory array, usually a ROM, to generate the required control logic signals. In a simple microcoded control scheme, we have the opcode of the instruction as well as the state information, which is conventionally kept using a counter as inputs to the control memory. These two inputs determine the address of the corresponding control word in the memory, which is also known as microinstruction. This way, we can generate all control words for each instruction and for each cycle and store them in control memory. As the instructions are executed, the corresponding control word will be pulled out and used to make the data pad perform the operation. So let's think about the following question. 2 to the 13 bytes, which equals 8 kilobytes. And we cannot put that much memory near CPU, right? Because control memory must be fast enough that must be in chip, built or manufactured in chip. But we cannot put that much memory, right? Instead, we can put logic and decrease the required memory consumption because most of the micro instructions are the same, right? So making the microcoded control smarter involves adding a few more registers as well as logic to calculate the next address generation. So here is what's going on. Control memory is dramatically reduced by storing only the unique control words, and the peripheral logic is used to calculate the next address in the memory to use. You can use micro instructions in consecutive order, or you can jump. Remember that we only stored unique control words, so it's inevitable that we jump from one micro instruction to another. Additionally, you can even write microprograms and compare the control words even more, yet you need to decode your program stored in memory. All these techniques became very popular in the control design communities due to the reduced control memory requirements of the microcoded control paradigm. Additionally, microcoded control allowed the CPU designers to change the functional description, specifications, type, and the number of instructions going forward. So it is basically, aligned itself with the backward compatibility requirements of the manufacturing all these CPUs, microarchitectures. A control memory could alternatively be a RAM, in which case it is called writable control store or control memory. All right, so in this class, we continued our discussions on single as well as multi-cycle computer microarchitectures. As you have seen, single-cycle computers are good for simple designs and provides nice and predicted outcomes. However, their performance is limited by the critical path delay. So the most time-consuming operation puts a bound on the clock frequency. If you remember our discussions on the CPU performance, this will adversely affect the parameters like instructions per second or seconds per instruction per second per program. On the other hand, multi-cycle computer breaks apart the critical path delay into smaller time slots and it allows us to increase the clock frequency. In this class, we have also seen hardwired control as well as microcoded control. and there are also pros and cons with each of the control design strategies. While Hardwired provides the fastest solution, it's not very flexible, and microcoded control is simpler to design, yet it might be slow for some workloads, although there have been huge attempts to make it faster and consume least amount of memory inside the chip. Anyway, so hopefully in the next class, we will dive into more interesting topics like memory basics and architectures. Please feel free to drop any questions you might have about today's class into my email box, and thank you very much, and I'll see you soon.